To announce about the Pi 2 thing, Rog?
Yeah, I'll do that on Friday.
Okay.
Yeah.
What are you announcing?
Well, just some work which Colin and I did with.
Oh, fine.
Right. Welcome everybody to the 12th, 10th. I don't know. Talk in this series.
We're losing count.
We're losing count. So without further ado, I will hand you all over to Lou.
All right, very well. Let me share my screen here. I'm back here for a few minutes in these remarks about quantum mechanics. And it was pointed out to me that that I should redefine my Mach-Zehnder interferometer, so I'm doing so. Here is the half-silvered mirror, and when the light goes through the mirror, it just gets transmitted. It doesn't get disturbed. Maybe not all the light goes through, but that's a good way to think about it physically. Upon reflection, it might flip its spin, or it might even get a phase change. And those are the two qualities for the half-silvered mirror that I redefine it to be. So when you have an upspin going in, it gets reflected to become a downspin. And when you have a downspin coming in, it gets reflected to be minus an upspin. That's for the half-silvered mirror. And when it's transmitted, it just gets transmitted identically. So that makes our Hadamard matrix, our H, have a little phase change right there. And this, of course, the formalism of this is essentially the same as the formalism that we had when we did this before, but the sign is in a better place for thinking about it physically than it was before. So if you like that better, then you can go ahead and do the calculation using that, and you will find that everything behaves very similarly, that when you do a Hadamard, the half-silvered, then you do an ordinary mirror, then you do a half-silvered, and you compose the matrices, you see that you get an anti-diagonal matrix, which means that if you had a spin up going in, you'll have a spin down going out. And if you had a spin down going in, you'll have a spin up going out. And when you go through the paths formulation, you find that you're getting the same results. If, for example, here are the paths for the spin up going in, and you get a reinforcement for spin down coming out, and a destructive interference for the spin up, and similarly for the other one. So this is a recommended device to go through on your own and analyze, because if you do this, you basically have seen almost all of the principles of quantum mechanics coming out of this gadget. And it certainly is better psychologically to think of transmission of the mirror as not disturbing anything. Better for your thought experiments. Here's another remark, a couple more remarks about quantum. If you want to know the probability amplitude for going from A to B, perhaps you know it by some means. But suppose you also know that there are a bunch of intermediate possibilities that could happen. You might go from A to C1, or from A to C2, or from A to Cn. Well, if that is a complete set of intermediate possibilities, then the probabilistic kind of rules for amplitudes tell you, and they're independent of one another, tell you that you get the probability amplitude for going from A to B by going through the sum from A to Ci and then from Ci to B. And this is just like the rule for independent probabilities. But you see that this entails even further rules. Let's suppose that there were an intermediate set of possibilities, Ci, and then as it went along, another intermediate set of possibilities, Dj. Well, then you would get a double sum. And after a while, you see if there were many, many of these intermediate possibility situations, you would be summing over all the paths that took you from A to B with certain weights coming from these intermediate amplitudes. So the idea that you should sum over all the paths that take you from one point to another is exactly this kind of thing. And you will see that you always get a path sum if you've broken the system down into intermediate possibilities. It just follows from the principles of quantum mechanics. Now, I wanted to say a couple more words about that, quantum mechanics. I wanted to remind you or show you where Schrodinger's equation comes from. So to do that, I'm going to walk backwards into a couple of equations due to Einstein and de Broglie. Einstein hypothesized in his work on the photoelectric effect that the energy is equal to Planck's constant times frequency. And this has to do with photons for Einstein. So energy and frequency are related in this way. And momentum and wave number are related by de Broglie, who thought of particles as having waves associated with them. So these two equations were then contemplated by a lot of people. And in particular, Schrodinger looked at what de Broglie had done and wanted to create a wave equation that would describe it, because after all, the idea was that waves would be associated with particles. That was de Broglie's idea, but he didn't write down a wave equation. And so Schrodinger examined this and wrote a number of papers, and what I'm telling you about is a very simplified line that gets you to the final result that Schrodinger came to after thinking about it for a number of papers and years. You can think of a plane wave like this, and here's the wave number, and here is the frequency. And you can say, well, if I had a wave and I want something like a differential equation, then I could attempt to obtain these quantities, the energy and the momentum, by differentiating the wave function. And you see that that can be done. For example, if I take IH bar d psi dt, then I get, there's a minus sign there, and I'm doing with respect to t, I get h bar omega here, which is the energy. So IH bar d by dt extracts energy from the wave, and minus IH bar d by dx, I don't know why there's a delta there, that should be just an ordinary d, is the momentum times the wave. Remember, momentum is h bar k. So by differentiating appropriately, you can extract the quantities that you want from the wave. So Schrodinger elevated that to a principle and said, we'll take that to be the wave equation, where we will associate an operator to the energy and an operator to the momentum. And those operators are the ones I wrote, IH bar d by dt for energy and minus IH bar d by dx for momentum. But there is something further that has to come into this brew, and that is this. After all, energy is given in the physics by 1/2 mv squared plus potential energy, kinetic energy plus potential energy, or at least that's a good example of the actual energy functional. And furthermore, the energy is equal to the momentum squared, that's m squared v squared, divided by 2m. I just rewrote it there. Now we already have an operator for momentum, so that tells us that there would be another energy operator other than the IH bar d by dt. And that would be h bar squared over 2m d squared by dx squared plus v, by putting in the square of the momentum operator, which I had on the last slide. Do you remember it? There it is. If you square that, you see, you get minus h bar squared d squared by dx squared. And we're getting second derivatives with respect to space. So that says that we can take that as the energy operator, and we get the interrelationship between time and space via this interrelationship between the two ways of thinking about energy operators. And that is Schrodinger's equation, IH bar d psi dt, which was extracting energy from the wave, is equal to minus h bar squared over 2m d squared psi dx squared plus v psi, which is the physical expression for the energy involving the momentum operator. And now that's a non-trivial statement, and you can look for solutions to it. And that's what Schrodinger did. And he, of course, in 3 dimensions, where the d squared by dx squared is replaced by the Laplacian. And then you find that you can model the hydrogen atom, and a lot of things all come together, and this turns out to be very successful. It's a very interesting way to get to a differential equation. If you think about it, it's very different from classical physical ways of getting to differential equations. You think of getting an equation that's quite non-trivial, like the equation for a vibrating string, and you do it by thinking about Newton's laws and little bits of mass and some constraints, and model and write down the differential relationships that you see from the geometry, and you get a differential equation. And most of the classical equations are of that form. Here, one is asking, what kind of information can I extract from a wave? And by playing a game that isn't obviously going to lead you in the right direction, it led Schrodinger in the right direction, and turns out to be a very good model for a lot of physics. So we end up with Schrodinger's equation. And there's a story about a cat, but I won't bother you with it. Questions on that so far? Okay. Then we talked about the Yang-Baxter equation and so on. And I was just filling in a little background there. So let me move now over to where I was, and I've forgotten where I was. I think I'm still telling you physics stories. Just a moment. We talked about piecewise linear state models. We talked about the Yang-Baxter equation with its angular parameter in terms of those models. And I think I didn't mention this. I had talked about unoriented Morse state summation models for quantum link invariance, but it's a good idea to point out now, if ever, that all of that can be made oriented, and then you get Pomfrey and other not polynomials and lots of different ones, depending on solutions to the Yang-Baxter equation. One way to do this is to have the cups and the caps very simple, namely diagonal matrices with some powers of a lambda on them. That's the kind of model that I wrote combinatorially for you before. And then, of course, the cups and the caps have to be inverses of one another, that being an index there in the middle, because you want them to cancel each other out. And that's what I wrote here. I made these two matrices inverses to one another. So this is a good cup or a cap to use. It's very similar to looking for a Markov trace. You have some extra parameter you need to work into the situation. And then there are swing moves like this. And the swing moves are telling you that the, oh my, might as well fix it right now. I have a tendency, oh, no, these are already fixed. I'm sorry. Yeah, when you switch across the swing move, you have to watch whether you have a left or a right M and so on, but I have indicated them with appropriate arrows. So you get these equations and the Yang-Baxter equation. And then what is the last thing you need to do in order to check that you have an invariant? when you are doing it with braids, which I didn't work out here, you need to check that the Markov trace property works, just as Roger was talking about when he talked about braids. Here, when you're working with these tangle category models, you have already set it up so that as braids, everything is working. The ordinary Reidemeister move is working, but you need to check the reverse 2 move, you see, because that's the extra thing that kind of sits in there like the Markov trace needing to be extra checked. And this is the reverse ordered, reverse oriented Reidemeister 2 move. And when you write that out, you find yourself rewriting things in terms of cups and caps. I'm not going to go through this in detail. And then finding yourself with a special equation that has to be satisfied, equal to the identity, something like an inverse. This multiplied by that should be equal to the identity. And there's some cups and caps in there. And you end up with this. If you then translate that into what you get when you have the lambdas for the cups and the caps, you get an extra condition, which is similar to the Markov trace condition, for the R's to satisfy in order for the model to work. And once this condition is satisfied, then the model will work and it will be an invariant of regular isotopy. So that's the way you get quantum link invariance at this level of having matrix solutions to the Yang-Baxter equation and trying to fit them together to make a state sum. You need to have a lambda which works. And the kind of model that I mentioned before is exactly that, the one that modeled the Humphrey polynomial. So that's our description of tensor network quantum link invariance. If you read Reshetik and Turayev papers, you will see that if you read the Turayev papers, they're close to this level. And if you read the Reshetik and Turayev papers, they explain something that we haven't gone into, which is how to use quantum groups to make the quantum link invariance by using representations of quantum groups. And I won't talk about that, at least not now. So that completes that part, that sketch. And then we talked about Vaughan's letter from long ago. And then I wanted to begin to talk about Witten. And before talking about Witten, I want to spend a few minutes telling you the story that Feynman told about how he discovered the path integral formulation. Now, up to this point in talking about quantum mechanics, I said, well, it's kind of obvious that you should sum over paths, but it isn't at all obvious in what way you would sum over paths to really get to Schrodinger equation to look at all possibilities out eventually. But that isn't where he started. Let me read what he said. This is from his Nobel lecture. I think it's very interesting. It's worth spending a few minutes listening to this. The character of quantum mechanics of the day was to write things in the famous Hamiltonian way, in the form of a differential equation. The Hamiltonian is what I wrote before, the expression for the energy, p squared over 2m plus v, which described how the wave function changes from instant to instant and in terms of an operator h. If the classical physics could be reduced to a Hamiltonian form, everything was all right. Now, least action does not imply a Hamiltonian form if the action is a function of anything more than positions and velocities at the same moment. If the action is in the form of an integral of a function, usually called the Lagrangian, of the velocities and positions at the same time, integrating over a Lagrangian here. Lagrangian that one uses in physics is usually kinetic energy minus potential energy. And classical physics I'm not reading from him, I'm talking. The classical physics turns out to extremize the integral of the Lagrangian. So you can get Newton's laws and other classical things from extremizing the integral of the Lagrangian over all paths that go from one point to another. And Feynman is looking for a formulation of quantum mechanics that would use the Lagrangian. Then you can start with the Lagrangian and create a Hamiltonian and work out the quantum mechanics more or less uniquely. But this thing involves the key variables, positions at two different times, and therefore it wasn't obvious what to do to make the quantum mechanical analog. So that didn't help me very much. But when I was struggling with this problem, I went to a beer party in the Nassau Tavern in Princeton. There was a gentleman newly arrived from Europe, Herbert Yela, who came and sat next to me. Europeans are much more serious than we are in America because they think that a good place to discuss intellectual matters is a beer party. So he sat by me and he asked, "What are you doing?" and so on. And I said, "I'm drinking beer." Then I realized that he wanted to know what work I was doing, and I told him I was struggling with this problem, and I simply turned to him and said, "Listen, do you know any way of doing quantum mechanics starting with action, where the action integral comes into the quantum mechanics?" "No," he said, "but Dirac has a paper in which the Lagrangian at least comes into quantum mechanics. I'll show it to you tomorrow." Next day, we went to the Princeton Library. They have little rooms on the side to discuss things. Maybe you guys remember what the Princeton Library, math library looked like long ago. If not, the somewhat more recent film about John Nash has some nice photographs of those alcoves. And he showed me this paper. What Dirac said was the following: there is in quantum mechanics a very important quantity which carries the wave function from one time to another, besides the differential equation, but equivalent to it, a kind of kernel, which we might call kx prime x, which carries the wave function j of x, phi of x, known at time t, to the wave function phi of x prime at time t plus epsilon. Dirac points out that this function k was analogous to the quantity in classical physics that you could calculate if you took the exponential of i.e. multiplied by the Lagrangian, imagining these two positions corresponded to time and time plus epsilon, I epsilon that was. So kx prime x is analogous to e to the I epsilon Lagrangian of the difference between the two position points divided by epsilon. That's a discrete derivative, comma x divided by h bar. Professor Yela showed me this. I read it, he explained it to me, and I said, "What does he mean they're analogous? What does that mean, analogous? What is the use of that?" He said, "You Americans, you always want to find a use for everything." I said that I thought Dirac must mean they were equal. "No," he explained, "he doesn't mean they're equal." "Well," I said, "let's see what happens if we make them equal." So I simply put them equal, taking the simplest example where the Lagrangian is 1/2 m x squared minus v of x. But soon found I had to put a constant of proportionality in, suitably adjusted. And when I adjusted that I got an integral over this Lagrangian along a tiny path, and just calculated things out by Taylor series expansion, and out came the Schrodinger equation. So I turned to Professor Yela, not really understanding, and said, "Well, you see, Professor, Dirac meant they were proportional." Professor Yellow's eyes were bugging out. He had taken out a little notebook and was rapidly copying it down from the blackboard, and he said, no, this is an important discovery. You Americans are always trying to find out how something can be used. That's a good way to discover things." So I thought I was finding out what Dirac meant, but as a matter of fact had made the discovery that what Dirac thought was analogous was in fact equal. I had then at least the connection between the Lagrangian and quantum mechanics, but still have with wave functions and infinitesimal times. So what he ended up finding was that if you integrate over all the paths from A to B of e to the I over h bar times the action, it gives you the amplitude. That's what he found. That he went from this infinitesimal step version to integrating, well, this is how it looks in his PhD thesis. Now, I thought it would be interesting for you to see even a little more, but we don't want to spend a lot of time on it. I wanted you to see what it looked like, what he put on the blackboard, because it's quite clear on reading his thesis that what he wrote on the blackboard for Yela is what he wrote in a couple of pages in his thesis. It's actually quite a bit of fun to look at it. So let's look at it for a moment And if you want to, you know, relax and not worry about this analysis, that'll be fine. But this is where he started with Dirac. And remember, there's this difference here between the two variables. And he makes a substitution for the difference between the two variables to be eta. So you get m eta squared, and there's the potential. And this is basically the Lagrangian. And he's going to integrate like that. And then he's going to expand things in Taylor series like that. I just want you to see the form of it. You could stare at it in more detail if you wanted to. Then he gets some integrals of a Gaussian type, e to the I something squared, and he knows how to integrate them from advanced calculus. And so he puts in the answers to those integrals and looks at his Taylor series and approximates it to throwing away terms of higher than order 2 in epsilon. So he ends up with this, and he ends up with Schrodinger. We just saw Schrodinger. So that's what it was like. You know, it's just go to this advanced calculus, he writes it out, and there it is. Very non-trivial. And that's where the path integral formulation of quantum mechanics comes from that interaction, so that you end up with this kind of situation where you integrate over all possible paths from one point to the other, and you know what to integrate. You integrate the action. That's way more sophisticated than at that level than just saying, well, it's obvious that we get a lot of combinatorial paths by thinking about all the intermediate positions. How does that interface with the limit geometry? And still, there's a mathematical problem here, which is how do you justify the existence of an integral like that? And that is not fully solved to this day. But in the case of the one-dimensional Feynman integrals, there are ways to do some of it by, for example, switching to a real integral by removing the I and using Wiener measure and so on. There's lots of technical problems involved with this kind of integration. But on the other hand, you can continue to work heuristically with these, and that is what people do. And so, indeed, oops, I didn't remove that from where I had it before. I'm sorry. Let's use the slideshow where I believe I did remove it. Yes, no, I didn't. Okay. I had placed that somewhere else. I want to say one more thing about integration, and then we're going to talk about what Witten did. If you don't know how to integrate by using measure theory, that's all right. Neither do the college freshmen that you teach. And what is it that you say to them? You say to them you believe in the integral, and that if you were going to integrate by parts and you had some boundary conditions where the functions were vanishing, then the integral of f would be equal to the integral of g if their difference was a derivative of things that vanish quickly at the limits. So I could say that two functions are equivalent if f minus g is a derivative, and I could say that that equivalence class represents the integral. So I choose in the back of my mind when thinking about these heuristics with functional integrals to make the move that I'm talking about the equivalence classes in that way. And then I can later ask the question, well, might it actually make some kind of numerical sense? This is not so far from what physicists do, but they aren't so worried about the definitions. You'll notice that what I'm saying is very elementary, right? For example, if I had a Taylor series for a function, then the function shifted by a constant would be equivalent to the function. And so the integral would be the same if I shifted it by a constant. And you use that principle when you are actually doing some integrals. So I'm going to have this in the back of my mind when I talk about heuristics of Witten's functional integral. Was there a question? Maybe a groan. Okay. So now I want to talk about Witten's integral. So this is the kind of integral that Witten considered, which is not integrating over paths, it's integrating over all fields. This is the quantum field theory generalization of a Feynman integral. And that term up there in the EIK over 4 pi S of MA, that's the Lagrangian. And we'll see what kind of an animal the Lagrangian looks to be in a moment. But it doesn't depend on a metric. And so from Witten point of view, you're dealing with something that's topological when you deal with an integral of this type. But we're going to look a little more closely at what happens when you move things around. The WK of A is a way of measuring the knot in the field. So you have a field on space, and the field is in fact controlled by some Lie algebra, and we'll talk about that in more detail, but perhaps not in too much detail today. I want to keep it schematic. And you have the idea that given a field on space and a knot sitting in space, you could somehow measure the way the knot sits in the field in space by walking a test particle, if you're thinking physically, along the knot slowly, letting it get changed by the field until you come back to where you start, and measuring the difference in the internal vector for the test particle between where it was at the beginning and where it is at the end. And you measure the difference by taking a trace. So the apparatus is looking like this. I added a name to something here. S of MA is the Chern-Simons Lagrangian. I'll write it out in a moment. And the W is the trace of what's called the path-ordered integral around the knot of the field. That, of course, is just representing is still abstract, but it's representing the idea of moving something around the knot in the field until you get back to the point where you started. Path-ordered because you have to keep track of order when you do something like that. So what does this bit of machinery actually look like? Well, the Lagrangian is the trace of A wedge dA plus 2/3 A wedge A. That's the Chern-Simons form. And never mind its more explicit version, but I did think that I had written a somewhat more explicit version of what a gauge field is in the next slide I did. Yes, okay. So this is telling you what a gauge field is as a mathematical entity. Local coordinates. There are some Lie algebra elements T upper A. That's a basis for some matrix Lie algebra. So that's very concrete. Choose your favorite small Lie algebra, SO3 or SU2 Lie algebra, and you have a set of matrices that generate it linearly independent. And then you can write an arbitrary element of the Lie algebra by summing some coefficients on A times the basis elements. And then if you ignored the K, that's what the A uppercase of A of X T upper A is. That's just a matrix A upper K in the Lie algebra. And then we're summing them with respect to the coordinate directions. And everything is a function of the point in space. So that is the field, the gauge field, or the gauge connection. It's probably better thought of as a connection than as a field. In fact, when you do the physics, it's really a connection. It's telling you how to go from one place to another. I'll say that more explicitly in a moment. And the curvature of it, excuse me, I thought it was there. It's on, I didn't write curvature until a later slide. So let me just go to curvature. Sorry, there. Curvature is dA plus A wedge A. And I wanted you to stare at that just so you see that what kind of a form curvature has. And why do I call that curvature? I call that curvature because that's what it is in the true differential geometric sense if you think of A as a connection. If you think of A as a connection, then it's a little differential change that can be made on a vector, the vectors on which the Lie algebra acts. So we're looking at a trivial bundle in this case over R3, and given a vector, which physically I would call an internal vector, all right, in some internal property of the particle. But I have this vector, which is of a different dimension than the three-dimensional space, and I can let A act on it. So if I have a vector at a point and I have a nearby point, then I take the parallel translate of that vector to be the vector plus A applied to the vector. And that gives me a nearby vector. And so I have a connection. And then I can consider what happens if I parallel translate around a tiny curve. And if you parallel translate around a tiny curve, then you find that the result of that is the curve gives you something non-trivial, and that's the curvature. And the curvature calculates out to be dA plus A wedge A. So that's why there's curvature here. And the curvature is the physical field. I can't emphasize that enough. That's where this all comes from for physicists, is that Yang discovers that he can re-express electromagnetism, maybe before Yang for that one, that he can re-express electromagnetism as a curvature. The physical field is a curvature of a gauge field. And then generalize it to other groups and other Lie algebras. So that's what the gauge fields are. The motivations for the Chern-Simons Lagrangian are, for Witten, very clear because it varies nicely with respect to the gauge field and gives rise to the curvature. But I won't go into the details of that. Here's our holonomy written out a little bit more. And here's the functional integral written out a little bit more. So now I want to talk about the measurement of the knot, what you do with the knot. That's the important point here. If you push the knot, or if you push a vector, parallel translate it around the knot, what will that do? I've written this symbolic expression, trace of path ordered, and so on. But what I've written below it is a concrete evocation of parallel translating around the knot. Because what I've indicated here is a product over all the points along the knot. What do I mean by that? I mean that you take a partition of the knot into some finite number of points, and you take the product of 1 plus A times, well, you take the product of 1 plus A, and that's just 1 plus A, that complicated expression. And you take a product of them along the ordered set of points. And if you were to apply that to a vector, then you are sequentially applying 1 plus A times the vector and going to the next point, and then evaluating at that point and applying 1 plus A times the vector, and you are shifting the vector along by parallel translation step by step until you come all the way back around to the beginning. I forgot to write trace on that formula. I meant to take the trace of it. But the expression that I wrote is the holonomy. It is what happens to the vector if you move it all the way around and bring it all the way back. It can be thought of as the limit of taking products of things in sequence. And so instead of writing an exponentiated sum, I write a formal product. These integrals can be justified. And then furthermore, I want to be able to think about the way the Wilson loop, that's this holonomy, W sub k of A. I want to be able to think about how does it vary if I varied the field. And a very useful way to think about varying the field is to think about it as a gauge functional derivative, which means, if you haven't seen this before, it seems quite strange, that each a upper I lower a of x is a different variable from your point of view. If you change the x a little bit, you'd be in a different variable. You have a continuum of variables here. And you could differentiate with respect to any one of them. In order to do this correctly, you need a Dirac delta function in there. You need distributions. But I will do it formally. So if I wanted to differentiate that, I think I have it on another slide. If I wanted to differentiate it at a particular x, it would change this product only at one point. And what would it do at that point? It would drop the a upper a sub I of x out of the picture because I'm differentiating with respect to it. And you'd get just the matrix t upper a dxi inserted into the line in the order of operations at a certain point. So at the next part of the slide, I've indicated formally a diagram that indicates putting a matrix into the line at a certain point. And that means that you would have the ordinary Wilson line, all its parallel translating going on, and one extra matrix positioned in a certain place. And you would be going along, parallel translate matrix, then you'd hit this matrix and you'd multiply by it, and then you keep on doing it on the other side. So remember that 1 plus a applied to b is parallel translation. And let's see what else I have managed to illustrate here. Yes. So I'm making up some symbols. You'll notice. The Lie algebra element is symbolized by a little box with an upper index. The derivative with respect to an a upper a sub k of x, one variable for each one of those, is written d upper a lower k, and the x is hidden. And then I can ask, well, what would it be like to differentiate a Wilson loop? And I'll go up to the Wilson loop at the top of the slide. And as I said, what it means to differentiate it in the AK and a particular X place is to knock that out. The 1 goes away and you just get TA dxi. So that means you insert into the line at a certain point a TA and a dxi, or a T or dxk, whichever. And that's what's indicated at the bottom here. The little triangle with a line on it indicates a dxk. It's a small bit of dx. Okay? And that gets inserted into the line. It's serious that you insert the matrix into the line because this is non-commutative matrix multiplication. The little differential can be moved around. It's a scalar wherever you like. I need one more formal item, and that is the epsilon on 3 indices. Our space indices, there are 3 of them, and the epsilon is the sign of the permutation ijk, or 0 if 2 of them are equal. So this is for determinants and volumes, and it is ubiquitous in doing 3-dimensional vector work. It turns out that the Chern-Simons Lagrangian, if you were to differentiate it with respect to the gauge field in this sense of indices, will give you the curvature tensor with its indices, which I have not worried you with, but there is a curvature tensor which expresses F, which is dA plus A wedge A. Specific index curvature tensor, just like the A's are specifically indexed. And the indices work out exactly right when you tie that thing into an epsilon. So you take the D and you tie an epsilon into the bottom, and you get the Chern, and you differentiate with that bit of formalism, you get the curvature. So you can get the curvature precisely out of the Chern-Simons Lagrangian. So we have these bits and pieces. And there's one more thing that we need to see. I'm leaving the details under the hood, of course, so you have some list of peculiar diagrammatic axioms about way things are behaving. If you vary the loop a little bit, so you look at what happens if you were to integrate along the knot, and then you make the knot change geometrically by a little bit of loop, and you look at the difference between the holonomy of one and the holonomy of the other, you just get the holonomy around the little loop. And the holonomy around the little loop is giving you the curvature. How does it give you the curvature? Well, it turns out that what happens is that that calculation is equivalent to inserting a bit of Lie algebra, that's the box, tied into the curvature tensor in its upper index, and the lower indices of the curvature tensor are space indices, and you have a dxi and a dxj. This is perhaps a little bit familiar in part because you know that curvature in differential geometry gives you curvature calculation gives you curvature tensor times a little area bit. And that's what happens here. There's a little area bit on the bottom, a dxi, dxj, but then there's Lie algebra here, and it's tied into that Lie algebra on the line. This can be verified. So now we have these bits and pieces. How the curvature comes in when you vary the line geometrically, how the curvature comes in when you differentiate the loop, and how you can differentiate a Wilson loop by getting an insertion of some Lie algebra. So we want to put this all together and see what happens. I'm reminding you on this slide that dxk is a little triangle with a k line, that the derivative of the Wilson loop inserts a bit of Lie algebra and a dx into the line, and that the variation of the Wilson line inserts curvature into the line. Okay, so these could be regarded as our axioms. And now I want to find out how the Witten's integral behaves when I vary the loop. So let's watch. I'm varying the loop at the top. That means that I insert curvature into the Wilson line. So I start by varying the knot line a little bit. I insert curvature into the Wilson line. There's a Lie algebra insertion on the Wilson line, and a curvature tensor, and a dxi and a dxj. But curvature is the derivative of the Lagrangian. So I can rewrite curvature as derivative of the Lagrangian, but it needs an epsilon. So now the dxi and the dxj at the bottom of that curvature tensor are tied into an epsilon. But the derivative of the Lagrangian could have been obtained by differentiating e to the k Lagrangian. And I have to have a 1 over k on the outside. So I can put the derivative over there on that function. This integral is an integral of a product of two things. So I integrate by parts. Boundary conditions are vanishing at infinity. I integrate by parts, changes the sign. The derivative is back on the Wilson loop. Now you know why I need to differentiate a Wilson loop. I differentiate it. That inserts another piece of Lie algebra and a dxi into the Wilson line at some other point. We have to think where. Now the Wilson line has two linked Lie algebra elements, and we're summing over all of the labels on that line that links them. That's a Casimir insertion if you're used to the Casimir element in the Lie algebra. And there's a dxi, another dxi, which is now attached to the epsilon. So you get the epsilon attached to three space elements. So it's a volume form. And that volume form had better be non-zero if there's going to be any change at all. If the volume form is 0, then we just calculated that there's no change. So that's a variational, somewhat axiomatic picture of how the Witten integral changes under a geometric deformation of the knot. So from the point of view of integration without integration, you can think of the following. that what I did was I started with the integrand e to the I k over 4 pi Chern-Simons Lagrangian variation of wk of a geometric. And I went through machinations involving derivatives and showed that it was equivalent up to a derivative of the Chern-Simons Lagrangian exponentiated times a volume form times a double Lie algebra insertion into the Wilson line. And then we have to look at the geometry to see whether that might be vanishing or not. So for example, oh, well, I didn't say it. I should say it when we're back on this slide. Under what conditions would the volume form be vanishing? Well, it would be vanishing, if you think about it, if you were doing a very flat Rademacher move and everything was almost in a plane, because then you're only changing things in 2 out of 3 spatial directions throughout all changes that you made. And as a result, you aren't creating any volume. So that means that we are concluding here in this heuristics that the Witten integral is invariant for Rademacher 2 and 3. In other words, it's a regular isotopy invariant of knots and links. On the other hand, there are deformations like trying to make a skein switch where you're using 3 dimensions. And the reason you're using 3 dimensions is a little tricky and worth thinking about, and then we'll stop. I just wanted to show you how it looks. Because you see, if you wanted to switch from the overcrossing to the undercrossing, then you would take the overline and you would deform it, deform it, deform it, and then at a certain point you would get it hitting the other line. It would be touching the other line, and then you would deform it down below. So the real question is, what happens when you deform it just up to the point where it touches the other line? At the point when it touches the other line, it's possible to have the Lie algebra insertion happen along both lines. I think maybe the best thing is to sketch this here and stop, and then we'll discuss it a little more next time. But it's possible to have the Lie algebra insertions on both lines. At that point, you will have differential changes in xi, xj, and xk. You'll have all 3. 2 dimensions from the movement of the line, which is moving in a plane, and 1 further dimension from the fact that you picked up a differential direction from the other line, which is moving off that plane. And so in that case, you would get something non-zero. And so instead of getting a 0 difference between switching from a positive crossing to a negative crossing, you get as the difference the result of Witten's integral with this Casimir insertion, this Lie algebra insertion into the line. Now, if you happen to be familiar with Vasiliev invariance, then you recognize this insertion of Lie algebra into the basic curve of the knot as representing, without further evaluations, a weight system, a Lie algebra weight system. And that, in fact, is what you're looking at. You're looking at the beginning of the transition to understanding invariance of this type by using weight systems and Lie algebra evaluations that are related to weight systems. Here, we're coming to it from the point of view of Witten's integral. So this is a good place to stop, and I hope that you found this skeletal picture of Witten's invariant interesting. The question of what is in that integral and what it means has been investigated in all sorts of different directions and explicated in all sorts of different directions. This is one line of bringing forth some parts of it. I'll stop here.
Oh, thanks, Lou. Well, there's some food for thought there. Are there any questions?
getting in my car the other day, I was wondering to what extent the GPS algorithm is some sort of a path integral.
The what algorithm?
GPS. So there were actually three possible roads to get from where I was to where I wanted to go, and realized that there were different
Oh, the
weights on the
GPS
path.
algorithm, I see.
It seems like a formal state sum, and I wonder if any of y'all have thought about that.
Have you ever studied operations research? They always confronted the question of having many pathways from one point to another in a combinatorial structure and finding the best pathway, right?
I see.
So they have lots of tricks for doing that, I presume.
Mm-hmm.
If you ask me if I've studied operations research, the answer is no.
Actually, I did some operations research as a holiday job when I was a student. Not that I remember anything about it. Are there any other questions?
I just want to add that the answer to the question is in a book by Leischerson and all on design and analysis of algorithms. They have algorithms for doing that. And I'll offline send the reference.
Great, thanks, Sam.
Sam, do they do something like integrating over all the paths in the system?
Sorry, I'm muted. I can show you where the answers are. Just a second. This is a standard book used in design analysis of algorithms. And the algorithms are actually in this book. It's been a while since I've looked at it, but we can talk about it sometime. I'm not prepared to talk about it now.
Mm-hmm. Who are the authors? Oh, just hold it up so we can all see the front of it.
Oh, okay. The answer, whoops, how's that?
Foreman, Liserson, Rivest, and Stahl.
Oh, there it is. That's better.
Thank you.
Thanks.
I hadn't thought about this being related to path integrals. That's an interesting idea.
Sam, would you, in some time in the future, would you be prepared to talk about this?
Well, thank you. Let me think about it and I'll get back to you on that. How's that?
That's fine. Yeah. Okay. So, are there any more questions? Okay, well, hope to see you all again on Friday at 6.